Everybody. So in the previous videos, right, we started a long time ago coming up with this idea of the derivative that we can use that we've associated to the slope of the tangent line and the instantaneous rate of change. And we learned a bunch of rules for taking them. And then we got into this idea of using the tangent line as an approximation to the function, right? So we're using the derivative to tell us something about the function. In the case of the tangent line approximation, it's like, what linear function does this thing look like? What does it behave like? There's another kind of behavior of a function that we can use our derivatives to help us understand, and these are extrema. So let's just start with some definitions of extrema. They are just maximums and minimums, the extreme values of our functions. Turns out it's a little more complicated than that. There's different kinds of maximums and minimums, and we'll get into all of that eventually. So let's start with some definitions, and then we'll do some examples. So we'll start with a function f. Let f be a function defined on an interval that I'll call I, right? It might be the whole real line. Really, it could be some collection of intervals, but it's simple enough to just think of one. And let C be a number in the interval I, right? So that just means C is in the set I. So I is some portion of the real line, right? All these values. We will say that f of x has an absolute maximum on I at C if f of C is greater than or equal to f of x for, I'll use some symbols here to shorthand this, for all, so there's an upside down A, means for all x that are in the interval I. Okay, so all the statement is saying is we start with a function, it's defined on some interval, and C is a number in that interval. Then we'll say this function has an absolute maximum on that interval if at this number C, the output of C is greater than or equal to all the outputs of f on that interval, right? So if I have, here's my interval, let's call it A, B. Maybe the function f looks like this. So if we're just talking about this little portion of the function, or maybe that's all it's defined at, right? Then this value here, if this is the number C, this is the point C, f of C. Notice that the output there is greater than all the other outputs on that interval, right? That's what this statement is saying. And then in a similar way, we say f of x has an absolute minimum on I at C if f of C is less than or equal to f of x for all x in this interval. All right, so pretty similar drawing. If I have some function on this interval, all right, maybe here's my value C. This point here, C, f of C, is smaller than all the other values of the function there, okay? So this is the idea of absolute maximum or absolute minimum. And we call the maximums and the minimums the extrema. So these are absolute extrema. We will see that this isn't the only kind. There are things called local maximums and minimums that we'll get into a little bit later. That have a similar but not precisely same definition and have a little bit different of a meaning. But we'll have to work for those. We'll work up to those. We're going to talk about absolute max and mins a little bit more before we get there. So let's do an example of an absolute maximum and an absolute minimum. So let's look at the function f of x is equal to negative x squared plus 4x minus 10. Okay, so this is a parabola. And if you recall how these work, notice that we have this negative out in front of the x squared. And so this is going to have is going to open downward, right? And if you think about that shape, right, upside down parabola, well, that's going to give us an absolute maximum at the vertex. So let's see what the vertex is going to be. If you remember your vertex formula, negative b over 2a, in this case, that's negative 4 over negative 2 is 2. And the output there, we get negative 4 plus 8 is 4, minus 10 is negative 6. So we have a vertex at negative 2, 6. Okay, and that would be our absolute maximum, right? If we look at this picture, like a quick sketch, or we can go to a nicer picture of the graph. Here is, let's see if it gives me, there it is. There's that vertex, right? All the other values of the graph of the function are below this one. So it is a maximum, an absolute maximum. We can see this algebraically if we rewrite this in vertex form. Since I have the vertex here, I know that this can be rewritten in the form negative x plus 2 squared. Oh, this should be negative. Sorry, I switched I'm just looking at this. I switched the negative. It's not negative 2, 6. It was 2 negative 6, pardon me. And we have a minus 6 there, right? So there's our vertex form, same graph, same parabola. Notice what we have here. If we think about starting with the number negative 6, and then we're adding, I'm just rewriting this another way. We're adding this other quantity. But what do we know about this quantity? Well, we look in here, it's something that's squared. So the x plus 2 squared is always going to be positive, or it's going to be 0. And then we have a negative in front of it, so it's always going to be negative, or it's going to be 0. So we're starting at negative 6. We're adding either 0, we do nothing to it, or we're adding something negative, making it smaller. So all the values that this function pops out are going to be negative 6 or smaller. Just what we saw in the graph, but now we have an algebraic interpretation of that fact. Notice this function has no absolute minimum, right? You can't pick a value that's smaller than all the rest. It just keeps getting lower and lower. If you tell me some value, right? If you tell me you think, let's go to that graph, right? Let's look at f of 100, gives me negative 9,610. Well, I can get smaller than that by going to f 101. And if you go out to some massive number, right, I can keep making it smaller by just taking larger and larger values of x and getting these larger and larger negative numbers. So there's no minimum here, right? A function doesn't have to have both of these, doesn't have to have either of them. We'll see examples of that later too. All right, let's do another example. Let's look at the function g of x equal to x squared over x squared plus 1. So as we move forward in these videos, we'll be able to look at functions like this and do some pretty good analysis to understand what they look like, their behavior, and all kinds of things. So we're going to do a little version of that here. I want to try to understand what this function's doing exactly. And if you notice, I can rewrite this. I'm going to use a little trick of adding 0 in the numerator. Right, I added 1 and subtracted 1, so that's like adding 0, and I can rewrite this as x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1, which is 1 minus 1 over x squared plus 1. Okay, so let's look at this thing. Let me rewrite it here so we have it in one place. This is the same function, just written another way. Let's think about a few things that are true for this function. First of all, the denominator of this fraction is always positive, right? It's never even 0 because we've got that +1 there. So x squared can't be smaller than 0, and we're adding 1 to it. So the smallest this denominator is 1. It's never going to be any smaller than that, right? Remember, the larger the denominator gets, the smaller the fraction gets. So as x gets further and further from 0, this denominator is getting larger and larger, right? Which means this fraction is almost disappearing. In other words, as x gets further away from 0, in other words, as it goes towards infinity, right? All I mean by that is x is getting to be larger and larger numbers. And actually, because it's being squared, it doesn't matter if it's positive or negative, right? If I put in x as -100, we square it, we get 10,000, and then I have 1, we get 10,001, and we have 1 over 10,001, very small. As x goes further along, we get out to -infinity, we square it, and add 1, we get a very, very small fraction, right? So as x is getting larger in both the positive and negative directions, this expression is getting smaller, right? So I'm going to write this arrow to 0, meaning it's getting extremely close to 0, right? We actually haven't done limits like this. This might be reminding you of limits that we did earlier. We didn't do limits like this, but we can do them. We will do them later, but this is a little preview of that. It should be easy enough to understand that as x gets incredibly large, positive or negative, this thing gets incredibly small, which means this thing gets close to 1, right? Because we're subtracting almost nothing. We're starting at 1 and we're subtracting almost nothing. So it's getting closer and closer to 1, right? As we go away from 0. Remember, 0 is the smallest this denominator is going to be, which means it's the largest this fraction is going to be. Let's just write this out. That 1 over x squared plus 1 is largest when the denominator is smallest, when x squared plus 1 is smallest, and that happens at x equals 0, right? Because at all those places it gets bigger. So we're taking away the most from 1 at x equals 0, which means it must be the minimum. G of 0 is going to be 1 minus 1 over 0 plus 1, or 1 minus 1, or 0. You can also put it into the original form of the equation. We get 0 squared over 0 plus 1, which is 0, right? And so this is going to have to be the smallest, because as soon as we start putting in numbers that are different than 0, it doesn't matter if they're positive or negative, we're subtracting something, we're subtracting less from 1, so we get closer to 1. So our picture now, oops, it's going to be something like this. We know this function when x is equal to 0, the output is 0. We also know this function is always less than the number 1, right? Look back at the original expression. We've got x squared over x squared. X squared over x squared would be 1, except we always add 1 to the denominator. So the denominator is always one number bigger than the numerator, which means it's less than 1, but it's really close to 1, right? If you put in 1,000 squared over 1,000 squared plus 1, you almost have 1, which is the same thing we were saying down here, that as x goes towards infinity, we're getting something closer and closer to 1. So our graph ends up looking something like this. This is an even function, so pretend I draw this. Ooh, I almost had it, and I got shaky. Should be a perfect reflection of itself over that line, right? That's what our graph is going to look like, okay? The important thing right now, that analysis might have been a lot at this point, but it's good to get experience with it. But now that we have this graph, we can think about maximums and minimums. The function g of x, has a minimum at x equals 0. The minimum is g of 0 equals 0. right? A couple of things to notice. One is they both happen to be 0 here, but x is the location of the minimum. The evaluation of the function is the actual minimum. If we go back to this other example, right? This function f of x has a maximum at x equals 2. The maximum is f of 2, which is -6, right? So we want to distinguish between the location of the minimum and what the actual minimum is. In this example, of course, they're the same number, but we still have these two meanings. This function does not have a maximum. 1 is not the maximum. There's no input I can get to get 1, so that can't be my maximum. Any number I choose less than 1, right? If I pick a number here that's less than 1 and think maybe that's the maximum, right? My function hits that number, but then it squeezes in between that number and 1. If we leave any space in there, it eventually gets close to that because this thing we're subtracting eventually gets so small that there's almost no space between our output and 1, but there's always some. And so we never actually achieve a maximum. We just continue to get closer to the value 1. Let's look at a nicer graph of this. So get rid of our parabola. Here's that function. Let's change our scale to make it a little more dramatic. So we'll go from -0.5 and let's do a maximum of 1.5, right? So my scale is pretty huge. We see this, there's that minimum. And then as we zoom out, right, at this scale, we can't see the difference between this function and the line y equals 1. Right, if I zoom in here, the difference between these is we've got, well, let's just evaluate it. What's f of 400? Oops, not f, I want g. G of 400, you see, is 0.99999375039, and on and on and on, right? We've got 400 squared over 400 squared plus 1, right? What's 400 squared? 160,000. So you've got 160,000 divided by 160,001, right? You're barely not 1, but you're not 1, and I can't see it even zooming in here. But oh, there we start to see the difference at this really small scale. You can see we're incredibly zoomed into this graph. Okay, so there's a function. We saw first a function that had a maximum and not a minimum. Now we've got one here that has a minimum but not a maximum. Sorry for all the quick scrolling around. Let's do one more example. Let's just do this one with a graph. Let's look at y equals cosine of x, right? It hits the value 1 over and over and over again. It hits the value -1 over and over and over again. We know it never gets bigger than 1, and we know it never gets smaller than -1. So what's the absolute max? Well, there's nothing in the definition that says C, let's go back to the definition, that C is the only number that hits this. Notice we have an or equal to in these definitions. So there can be other values that have the same, there could be other places that have the same maximum value or minimum value, and those are just other maximums and minimums. And so with a function like cosine, right, where we have, let's do just a little piece of it. All right, I'll make this one, for instance, is at 0. 0, 1. There's another maximum over here at 2 pi 1. We've got a minimum over here at pi -1. We've got a minimum over here at -pi -1, and it keeps going, right? -2 pi 1. So we could say that y equals cosine of x has absolute maximums of 1 at x equals So notice it's just going to be all the even multiples of pi. If we kept going, it's 2 pi, 4 pi, 6 pi in the negative direction, same thing. So we could write something like at x equals 2n pi, where n, and this just means n is an integer, a whole number, right? So -1, all the negative integers, all the positive integers. If you multiply them all by 2, you get all the even integers. And so that's telling us we have a maximum at all of these different places. And then it would have, it has absolute minimums of -1 at, and now it's going to be x equals 2n minus 1 times pi, where n is in the set of integers. Same thing, if 2n is all the even numbers, right? So if you take the list of numbers from -infinity through -3, -2, -1, 0, 1, 2, and you multiply all of them by 2, you get negative, well, you can't multiply to infinity, but you see, right, you get -2, -4, -6, and in the other direction, you get 0, 2, 4, 6. If we just subtract 1 from all of those, we get all the odd numbers. And so this tells us we have all these maximum minimums, absolute maximum minimums, shared, they all have the same value, and so that has multiple, and in this case, infinite maximums and minimums. Okay. What about, let's just do a couple intuitive examples where we don't have, let's do one example where we don't have a maximum minimum, right? I'll just do it by drawing this. Like if I have a function like y equals x cubed, for instance. Oops. Here's my axes. We know that this looks like something like this, right? And so it keeps going up into the positive numbers as high as we want on the right. It's down into the negative numbers as low as we want on the left. And there's no limit to that. There's no end to how high and low they go. So there's no maximum or minimum, right? Or you might have a function, let's say something like this. Like 1 over x. Right? It doesn't have a minimum because it just keeps going down to the negative. We've got this asymptote and it's approaching, goes as far down negative as we want on the left as we approach 0 from the left, and it goes as far up towards infinity as we approach 0 from the right. And so there's no max or no min. Or even just a simple function like this. If I have the function y equals x on the interval 1 is less than x is less than 2, right? What does this graph look like? Well, it starts at x equals 1, the output would be 1, but it doesn't include these 2 points, right? So the fact that it doesn't include these 2 points means there's no max or min there. What's the minimum value? You want to say 1, but it doesn't actually hit 1 because we've got this restricted domain, right? And what's the next number bigger than 1? Well, there isn't one, right? What's the minimum value? 1.01, but then I can get closer to 1, and I can keep getting closer and closer and closer and closer and closer to 1, and there's no end to how close I can get. So there's no smallest value. There's no number right next to 1. There's an infinite number of numbers between 1 and any other number, and so there's nothing. There's no smallest one there, and the same thing happens as we approach 2. So when do we know we're going to have a max or a min? Well, here's one set of conditions that when we have them that are sufficient to prove that we have a maximum or a minimum. There are other ways in which you can have it, but this is one we often look for, and this is something called the extreme value theorem. Okay, so we say that if f is continuous on a closed and bounded interval that I'll call AB. Then, here, let's use a fun symbol. We're going to say there exists. There's a symbol for this. There exists, this backwards E tells me there exists a point C in the interval. So there's some fun symbols. So all that's saying is if f of x is continuous on a closed bounded interval AB, then there exists a number C in that closed interval at which f of x has an absolute maximum. Likewise, there is a point in the interval at which f has an absolute maximum. Minimum. We already did maximum, minimum. All right. All this is saying is the following. Here's an axis. Here's my closed interval. So the function is continuous on this closed intervals, including the endpoints. This is important. So that means the function takes on some value at the endpoint and it takes on some value at the other endpoint. They might be the same value, they might not be, it doesn't matter. All this theorem is saying is, intuitively, my function is continuous. So I need to draw a continuous function between these two dots, meaning I can't lift up my pen, right? No matter how I draw it, right? Any option I come up with to draw it, there's a maximum and somewhere there's a minimum, right? In this first one I drew, there's a maximum there, a minimum there. In the second one I drew, this straight line, the maximum is on the endpoint, and the minimum is on the endpoint, right? And then the last one, the maximum is up there in the middle, the minimum would be on the endpoint again, right? So you can try drawing this any way you want. It's always going to have a maximum minimum. There's even the sort of, well, in one sense, trivial example, but it also makes a good point. What if our function is just a straight line? Then every point in the interval is an absolute maximum and an absolute minimum. Remember the definition, it's an absolute minimum if every other value is less than or equal to it. And if I pick any point in here, every other value of the function is less than or equal to that value. And every other point is greater than or equal to that. They're all equal, right? So the whole thing is maximums and minimums. It's important. All these little pieces are important. The closed and bounded, we're not going to worry too much about in this course. It just means we can't have some kind of infinite interval or a collection of intervals that becomes infinite. We don't need to get down into the details of that. We're going to be thinking mostly of single intervals like this, a little segment of the real line. It needs to include the endpoints. Let's see what could happen if it doesn't, right? Here's a function that's continuous on, let's do a real example. How about we look at tangent of x on the interval negative pi over 2 to pi over 2. So here's negative pi over 2. Here's pi over 2. Zeros in the middle. Tangent is defined it's not a very good asymptote. Tangent is continuous in this whole interval. That's a typical drawing. Here we go. Tangent is continuous in this whole interval. So if we look at tangent on the interval negative pi over 2 to pi over 2, it's continuous on the whole interval except at the endpoints where it's not defined. then it doesn't have a maximum minimum because it goes down to negative infinity on the left side. In other words, it approaches negative infinity, or that's even silly to say. It gets larger in the negative direction without bound, and larger in the positive direction without bound at these two asymptotes. So there's no maximum value or minimum value, right? So without that continuity at the endpoints, this function fails. Now, it doesn't mean if we don't have continuity, we can't have a maximum minimum. It just means if we don't, we can't guarantee it. For instance, here's a function that's not defined on the endpoints, but it does have a maximum and a minimum. Here's my maximum, here's my minimum. The point I'm trying to make is if we're not defined on the endpoints, not continuous through the whole interval, we can't guarantee, which is what this theorem does, we can't guarantee that there's a maximum and a minimum. Let's look at one other way in which it could fail. It helps us understand what's important about it, I think, to see how it breaks. Here's another interval. What if we have a discontinuity inside the interval? So here's my function, it's defined there, maybe it's defined here on the interval, on the endpoint, and it has a jump discontinuity, and it's not defined there even. This function won't have a maximum or a minimum, right? Because as we approach this open circle, there's no highest value. We just keep getting closer to what that is. And the same thing happens at the bottom. If the function is defined here, now it does have a minimum, but it still doesn't have a maximum. We can't guarantee a maximum because that discontinuity allows us to get away without having one. Again, I can draw a discontinuous function that does have a maximum or minimum. Right? There's my minimum, there's my maximum, and it has a discontinuity. We just know that if it's discontinuous on the interval, somewhere in the interval or at the endpoints, it's not guaranteed to have a maximum or a minimum. Okay, I've said maximum and minimum enough. Let's end it here. There's more topics to discuss in this Extrema discussion, but we'll save it for another video. We'll look at how we find these points, these maximum and minimum points. We've seen a little hint at how we might, but we haven't really used any calculus to do it. So we'll get into that in the next video. Okay, thanks everybody.